In this example, we would like to find dy dx if x squared plus y squared squared is equal to 50xy. The graph of this curve, it looks like a figure 8 sideways here, a little bit like that. It's called a lemniscate. And finding dy dx involves, it means we're going to be finding the slope of the tangent line at a given point. And even though this graph is not a function of x because it doesn't pass the vertical line test, we will be assuming that y is a function of x here. And the reason that's okay is because if you want to find the slope of a curve at a point, you don't actually need the whole curve. You just need a little sliver of the curve. Just that little sliver of curve there is enough to find the slope of the curve at that point. And so globally, the equation does not represent the graph of a function, but locally it does. And that's good enough for our computation. So we're going to use implicit differentiation. The key is to take the derivative of both sides. So the derivative of x squared plus y squared squared will equal the derivative of 50xy. The derivative of x squared y plus y squared squared is going to be obtained by actually squaring this first. So using the FOIL method, I'll end up with x to the 4th plus 2 x squared y squared plus y to the 4th. I just squared x squared plus y squared there. And that equals, on the other side, I'm not going to do anything, just the derivative of 50xy. Okay, so now on the left side, the derivative of x to the 4th is 4x cubed. The derivative of 2x squared y squared requires the product rule. The first, which is 2x squared, times the derivative of the second. The derivative of y squared is 2y times dy dx from the chain rule. And then plus the second, which is y squared, times the derivative of the first. The derivative of 2x squared is 4x. And then moving on to the third term on the left side, the derivative of y to the 4th from the chain rule is 4y cubed times dy dx. And on the right side, the derivative of 50xy, we use the product rule. 50x is the first function and y is the second. So the first, 50x times the derivative of the second, that's dy dx, plus the second, which is y, times the derivative of the first, which is 50. So we have this rather large equation here with many terms, including terms that have a factor of dy dx. So we now solve this equation for dy dx, and that'll give us our answer. So the terms with dy dx we'll put on the left. So we have here a dy dx term that's coefficient 4x squared y times dy dx. We have another dy dx term here, so that's plus 4y cubed dy dx. And then we have another dy dx term on the other side of the equation, so we have to move it. So we have minus 50x dy dx equals, on the other side, 50y is on the right already, so just copy that, 50y, and then 4x cubed has to get moved over, so minus 4x cubed and minus 4xy squared. So now all the dy dx terms are on the left. The point of that is that we can factor out dy dx. So we have dy dx times 4x squared y plus 4y cubed minus 50x, and that's equal to, just copy the right side, 50y minus 4x cubed minus 4x y squared, and now we're basically there. dy dx is obtained by dividing. It's the right side divided by the quantity in the parentheses. So 50y minus 4x cubed minus 4x y squared divided by 4x squared y plus 4y cubed minus 50x. And this fraction can simplify a little bit. We can factor out a 2 on the top and the bottom and cancel the 2. So we'll be left with 25y minus 2x cubed minus 2xy squared. And on the bottom, factoring and canceling a 2 will leave us with 2x squared y plus 2y cubed minus 25x.